So now we're going to talk about actually simulating, generating a sampling distribution. So this is the idea of how do we go from that known population and generate, right, create a sampling distribution. Well, one way you could do it is you could use what's called simulation. You could use computer programs, typically, to literally take samples, random samples, over and over and over again and create a sampling distribution. So an example of a data set that you might do this with is something like this. So here we have an experimental design. We want to know if hamsters who get normal amount of sleep versus less sleep, which will experience more stress, right? And maybe we have a hypothesis that having less sleep leads to greater stress, right? So we're going to look at the independent variable of sleep, right? Either regular or less sleep. We wake them up, wake the little hamsters up. And then the dependent variable that we might look at is their stress hormone levels, right? So let's say we tested these hamsters. So 3, 6, 9, 10. So here's 10 hamsters in our lab, right? And 7 of them were in the regular sleep group, and 3 of them were randomly chosen for the less sleep group. And this is their resulting levels of stress hormone. What we want to know is, are these less sleep hamsters, are these insomniac hamsters, are they more stressed than you would expect by random chance, right? That's what we expect. And so the known population that we could think about is something like, these are randomly selected stress hormones. Randomly selected hamsters, right? That these 3, it's not that they're more stressed, it's just that by chance you might get these numbers to be in there anyway, right? And so we might randomly select, through a computer program, 3 of these numbers, 3 of the entire set of hamsters, so randomly select them and generate a sampling distribution. And maybe one thing we might want to do is get their means, right, of 3 hamsters at a time, right? So pick 3 random hamsters, get their mean, put it in my sampling distribution. Get 3 random hamsters, get the mean, put it in my sampling distribution. Over and over again, right? Until we get a whole bunch of means. Like, here's like a dot plot of a whole bunch of means, right? And the means might range from 25 all the way to 64, right? So the mean can't be it can't be equal to or greater than 64. It can't be less than or equal to 25, right? It has to be somewhere in between. All right. And then we want to know, okay, now we have these less sleep hamsters. Sleep-deprived hamsters. That makes more sense. So sleep-deprived hamsters, right? And so maybe we'll calculate their mean. And so we could calculate their mean. So that's 55 plus 55 plus 64 over 3. So 58 is their level of stress hormone. So here we have X bar as 58. And we want to know, is this likely or unlikely given this sampling distribution? Right? So we want to ask, likely or unlikely? Right? If it's likely, then we might say, oh, no, it's just, we can't separate whether this is due to less sleep or it's due to chance, right? But if it's very unlikely, we might say, oh, we don't think it's randomly selected. It's not that you randomly selected these hamsters. unlikely that you randomly selected these hamsters. It's more likely that something special's been done to them. And we know what that special thing is. It's that they've been deprived of sleep. And in that way, you can make some conclusions, right? Now, you can't necessarily say for certain whether sleep causes hormone levels to rise. It's not that you looked at the mechanism and saw the sleep causing the hormones to rise. It's not necessarily that. But you can say whether this is a likely sample given random processes, or you could say it's unlikely given random processes. And that's really all we can know from this kind of logic, right? But that kind of logic will still take us far. All right. So here we go. Here are all our hamsters, and here's our known sample of less sleep hamsters. So it's this guy, and, or I don't know if that's that guy. Maybe it's that guy. Who knows, right? So it's those guys, right? But, maybe it's just that they were randomly picked. Who knows, right? In order to generate this sampling distribution of the mean, right? Here's what we did. First, I'm really just summarizing in steps what we talked about before. So first what we did was take random sample of 3 hamsters. And here we'll call that n, right? Because n is the size of the sample. Then what we did was we computed a summary statistic. We computed the mean, right? But, we could have computed standard deviation. We could have computed, median, right? So some summary statistic, right? And then number 3 is the important step. Repeat steps 1 and 2, right? So you do this over and over again, and that's what it means to simulate a sampling distribution. And the 4, examine and plot resulting sample statistics. So here, these are all means, right? So that's a mean, that's a mean, that's a mean, right? It's a mean of 3 that have been selected, right? And so if we repeat this, if we repeat these 2 over and over again, and then we plot it, then we'll see the distribution of samples, of sample statistics, right? And that's why it's called a sampling distribution. Ta-da, right? And so once we have a sampling distribution, then you could see, oh, it has a expected value. We could find the mean of this thing, right? It's like a meta mean. It's the mean of means, right? And we could find the standard deviation of this thing, right? And so that's what we mean by expected values. Okay. Okay, so now let's compare these 2 things. So we know the logic of probability distributions. Now let's apply that same logic to sampling distributions. All right, so here we go, known population to fair die, probability distribution. It's the same thing, I just made it sort of small. Here's a likely sample, here's an unlikely sample, right? And we know it's likely by looking at this probability distribution. We know this is unlikely by looking it up in this probability distribution. Okay? So pretty straightforward. What about in terms of this hamster stuff? So the known population is all the hamsters in our study. Not only that, but our mechanism is just like here we think it's 2 fair die. Here we think it's all hamsters, and they were 3 chosen randomly, right? We could simulate that process, right? We could choose 3 randomly, and find a sampling distribution. And these are all means now, right? Not only that, but we could find a likely sample, which might be something like, 47, So if we found that we found a mean of 3 hamsters, so our sleep-deprived hamsters had a mean of 47 in their stress hormone levels, we might say, well, it seems very similar to chance, right? So it seems like they're not that different from just picking hamsters at random, right? But we might have an unlikely sample. And here we had, in the example I showed you, we had 58. And 58 is over here. And that might show us, that's really unlikely that we would choose 3 hamsters at random and get such a high mean, right? And so in that sense, we could start thinking, oh, okay, this is likely to have come from random generation. This is less likely to have come from random generation. All right. All right, so we talked about the very specific method of simulating sample distributions, like take 3 hamsters at a time, compute their means, right? Now I'm just going to say that those same 4 steps, but I'm going to say it in just more general terms. Take a random sample of size n from the population, right? Whatever your population is, whatever your n size is, your sample size is. Then you compute a summary statistic, and this could be the mean, median, it could be mode, it could be variance, right? It could be a whole bunch of different things, right? So all those summary statistics we talked about earlier, it could be any one of those things. Then you repeat 1 and 2 many, many times. And that's the simulation part where we're pretending to do this many, many times, right? And that's why it's really helpful that we have computer programs that can help us do this many, many times. And we don't have to actually draw, beads from a hat or something. And then finally, we want to display and examine the distribution of sample statistics. So we'll have a whole bunch of means, right? Or we'll have a whole bunch of variances or a whole bunch of standard deviations, right? Or interquartile ranges, whatever you want, right? And in that way, this is the general method of simulating the sample statistics. Once you have that simulation, this is how to go from, so this part is going from the known population, and usually the known population is the random process. That's sort of the default. Because it's hard to generate like non-random processes, but it's really easy to generate random processes, right? And then we get our sampling distribution, right? So this part is this arrow right here, simulating. I'll put simulate, right? So that's that part. Now, there's another part. And that's the part where we now compare to sample, right? Or rather, we compare sample to the sampling distribution, right? And we decide likely or unlikely. Right? So that's another part that we haven't talked about here. But in order to do this, what you need to do is compute the summary statistic for your sample. So if you have a whole bunch of variances here, you need to, compute variance for your sample, and then you compare it to your sampling distribution. And we make a call. Is it likely? Is it unlikely? All right, but even though we know all this stuff, there are still some little bugger questions that remain. So in these cases, we know what the population looks like, right? Like we have like a group of hamsters, right? And we know what it looks like. And we're generating these random processes, right? So what happens when we have no idea what the population looks like? We don't have a nice list of 10 hamsters. What if we want to know stuff like, what if you randomly draw from any high school student in the US? We don't have all those numbers, right? Like, in order to do the sampling process, you would have to have, all the giant list of, all the, let's say, GPAs of high school students in the US and then pull randomly from them. What if you don't have that population? Then you're screwed, right? Also, can we have sampling distributions for summary statistics other than the mean, right? Because we've only really looked at the one with the mean, right? And what do those look like, right? So we have a sort of answer for this, yes, but we want to know, can we just pick one randomly? Like, how do you know which one to use? And then the third sort of unanswered question is, how do we know whether a sample is sufficiently unlikely? So far we've been just eyeballing it. Like, we look at it and we say, that seems unlikely. 2%, that seems unlikely. 5%, that seems unlikely. 10%, that seems more likely, right? We're just like making a judgment call, right? But how do we know whether it's truly unlikely or it's just our opinion? So do we always have to simulate a large number of samples in order to get a sampling distribution? Because that seems like that's going to be really hard to do, right? And so these are just some questions that remain, but we just went through the intro, so these will be answered later on, hopefully to your satisfaction.